All right, today we're diving into the really fascinating world of reverse engineering. We're going to peel back the layers of a computer program to see what's really going on under the hood. And we'll kick things off with the simplest program you can possibly imagine. So, we've all seen the classic Hello World program, right? But have you ever stopped to think about what that simple line of code actually looks like to the machine that's running it? The answer, well, it might surprise you. To figure that out, we have to start at the very beginning, with the code that we as humans actually write and understand. Here it is, a super basic program written in C. It's clean, it's simple, and for a human, it's perfectly readable. And C is a big deal because a ton of the operating systems and major apps we use every single day are built with it. Now, to turn our readable C code into something the computer can actually use, we need a special tool called a compiler. This command here, GCC, it takes our code and translates it into an executable program, basically a language of ones and zeros that the processor can understand and execute directly. So our code is compiled, but what does that really mean? What does the computer actually see? To find out, we have to dissect the program itself. We can look under the hood using a process called disassembly. What this does is it takes those raw machine instructions and translates them back into a slightly more readable format called assembly language. You can think of it like translating the computer's native language back into something we can at least start to make sense of. And wow, this just shows you the difference perfectly. On the left, you've got our simple one-line command. On the right, that's the assembly code the computer is actually executing. It's a completely different world, isn't it? Our one little printf function suddenly becomes these cryptic instructions about moving data around in the computer's memory. Yeah, it can definitely look intimidating. Cybersecurity expert Steven Sims puts it really well. Learning to read assembly is just like learning any new language. At first, it's all just noise. But with practice, you start to see the patterns, you start to understand the grammar. Okay, so now that we have a feel for the language the computer speaks, let's introduce a tiny little crack in the code. We're going to see how one small, almost innocent-looking change can create a massive security problem. In this new version of our program, we've added two things. First, this little box in memory called a buffer. It's designed to hold 16 characters, let's say, for a user's name. And second, we're using this function strcy to copy whatever the user types into that box. And right there, that's the problem. As Steven Sims calls it, this is the bad command stir copy. It's notoriously dangerous. And why? Well, because it has one fatal flaw. It never ever checks how much data you're giving it. It'll just keep on copying and copying and copying. This leads to a classic, and I mean classic, vulnerability called a buffer overflow. If a user gives the program more than 16 characters, SCTRPY doesn't care. It'll just happily keep writing past the end of our little 16-character box, spilling over and corrupting other critical parts of the program's memory. So what's the big deal? What actually happens when that data spills over? What's the consequence when we break the stack by just feeding the program way more data than it was ever built to handle? Well, an attacker isn't going to type in a normal name. Instead, they might use a simple script like this to send 32 A's as the input. That's double the size of our buffer. And boom, the program crashes. But it doesn't just die silently. It gives us this very specific, very angry error: stack smashing detected. The program itself figured out that its internal memory, the stack, was messed with. It was overwritten or smashed. Here it is, side by side. You give it a normal, short input like monkey, and hey, it works perfectly. But give it that oversized, malicious input, and the whole thing breaks. That right there is the buffer overflow in action. So why did it say stack smashing detected instead of just, disappearing? Well, it's because modern compilers are pretty smart. They automatically stick in a defense mechanism called a stack canary. Think of it like a secret tripwire. It's a random number placed in memory right next to our buffer. Before the program finishes up, it checks to see if that secret number is still there. Our overflow of A's wrote right over it, which set off the alarm. Now, all of this might just seem like it's about hacking and breaking stuff, but understanding these really low-level details is absolutely crucial if you want to build secure and reliable software. This is exactly why we look inside. It lets security pros dissect malware to see what it does. It helps developers find these dangerous bugs before the bad guys do. And maybe most importantly, it gives us a powerful way to truly understand the complex, hidden tech that pretty much runs our entire world.
And that really leaves us with a fascinating question to chew on, doesn't it? In the millions and millions of lines of code that run on your phone, on your computer every single day, what other secrets, what other flaws, and what hidden behaviors are just sitting there, waiting to be discovered?